you'll see that it's got how many equilibria? How many equilibria do we see? If I solve for dy dt equals 0, how many solutions do I get? 3. What are they? So it's y equals 0, y equals 1, or 3 over 2y is equal to a half. And that means y is equal to a third. Because if y is equal to a third, 3 times a third is 1, so it's a half minus a half. So I get 3 solutions. So now if I take this function and I differentiate it, I use the product rule. It's got 3 factors. So it's this times the derivative of that, this times the derivative of that, or the last 2 factors times the derivative of the first. So I can write these out, and then I can evaluate the derivative when y is equal to 0. So this is the derivative. I put y equal to 0, and I get f dashed 0 is a half. So what does that mean about 0? Is it stable or unstable? It's unstable because the derivative is positive. Now if I do the same if I put y equal to 1, I get f dashed 1, and I put y equal to 1, that goes away, I evaluate this, I'll get the number 1, which is also positive, so that's unstable. But if I put y equal to 1/3, which is my third equilibrium, that turns out to be stable. So the equilibrium y equals 1/3 is stable. So if y represents the proportion of doves in the population, what this says is that when you have hawks and doves, and every time, and the rewards are worth 2, but the cost of fighting over a reward costs you 3, then being a hawk is expensive when you meet another hawk, but is great when you meet a dove. But doves can still persist in the population at a frequency of 1/3. So what this says is that here is 1, here is 0, and here is 1/3. And this is the proportion of doves. So it says that if the whole population consists just of hawks, imagine we have a population of hawks, and they just go about their business fighting and getting resources. Gradually, they'll just wear themselves down because they'll be continuously fighting over, and they'll always get less than it's worth fighting about. But that's the situation. Now, a small group of doves come in. Then, because every time the doves meet each other, they can get some reward, it turns out that they will grow in... Now, if everybody is a dove and a hawk comes in, that's great, because you don't meet other hawks if you're just one hawk, and every time you meet a dove, you win. So then more hawks will come in. And if almost everybody's a dove and there's just a few hawks, then most of the time hawks will be fighting doves and just winning, and then a few rare occasions they'll meet each other. It'll definitely be worth being a hawk when there are very few doves. And what this dynamics tells you is that hawk populations will grow when there are only doves, and dove populations will grow when there are only hawks, and they'll come towards an equilibrium in which 2/3 of the population are hawks and 1/3 of the population are doves. Now, if the reward system is different, like if V was equal to 3 and C was equal to 2, then what would happen? Is it possible to get hawks and doves to coexist? Well, I don't know the answer to that. You have to work it out using this method. Okay. So basically what we've done up till now is we've worked in 1 dimensions. We've talked about discrete models. We've looked at some interesting applications. We've looked at genetics. We've actually extended our analysis to 2 dimensions in the discrete model, where we looked at a host parasitoid. We talked about the dynamics of models in general and how we've shown that sometimes they're stable, sometimes they have chaotic solutions, sometimes they have cyclic solutions. If you have differential equations, what we showed is that a first-order differential equation, if it's nonlinear, can have equilibria, but you don't get the chaotic or the periodic behavior. You just get stable and unstable behavior. And if you look in 1 dimension at the logistic equation, we can develop ideas about harvesting. Now, what we haven't done yet is we haven't gone to 2 dimensions to discuss differential equations, because that's a little more complicated. And so, except when we said we talked in the context of compartmental models of having more than 1 differential equation, but we didn't say anything about how to analyze them. And ultimately, what you're going to do is you're going to solve them using your NOVA software, because you can easily just integrate them. So you can build NOVA models of differential equations with more than 1 variable very easily. But we haven't talked much about the theory of differential equations with more than 1 variable. In order to get into the theory of differential equations with more than 1 variable, we have to beef up the tools and discussion that we've been having. So here we talked about the phase line. If we have differential equations in 2 dimensions, instead of having phase lines, we have something called a phase plane. And we're going to talk about how to analyze and do this in the context of prey-predator models and competition. We're also going to take discrete equations, and we're going to ramp them up in the context of putting age structure into the model, so that we can talk about equations in which you have several variables. And in order to do this effectively, we have to talk about matrices. Now, some of you have probably never done anything with matrices. Who's never done anything with matrices? Okay. So basically, I'm assuming that I'm not assuming that you know anything about matrices, and we'll start from ground zero in developing ideas of how to build matrix models in the context of populations with age structure. And then we'll get into ecological ideas in terms of differential equation models in the context of 2 species competing for resources or prey-predator interactions, and ultimately also disease modeling. So in disease modeling, a population is usually divided into several disease classes. So you have individuals that are susceptible, individuals that are infected but not yet infectious, individuals that are infectious, individuals that got infected, became infectious, and either died or survived, but once they survive, they have a certain level of immunity. Or individuals who are susceptible but are then given a vaccination and have some immunity. So we're going to talk about those kinds of models, which is highly relevant in these days of Ebola and the idea of vaccinations and influenza and all that sort of stuff. Okay, so any questions? This sort of, yeah? No, it's only up till lecture 11. everything up to lecture 11. This is lecture 12, including lecture 11. Yeah.
So the whole definition for stability continuous functions would not be yes.
It would.
It would.
Well, you mean linearization? I wouldn't talk. There's nothing. I mean, I've talked about stability, and I've talked about that result many times. So knowing the result, but asking you to derive it using a linearization, no. And the idea here is that we've talked about the conditions in the discrete and continuous, and the reason why I'm formalizing it now is that when I go up to higher dimensions and we're talking about differential equations in 2 or 3 variables, then it's good to have this basis. But no, I'm not going to ask you about the theorem per se in terms of how to derive it using linearization, but I expect you to know the result. I expect you to know that an equilibrium is stable if the derivative is negative of the function evaluated at the equilibrium. It's unstable if the derivative is positive. Because we've talked about that from day 3 onwards. Just about. Yeah. Anything else? Okay, so remember to bring a large book, and you'll have a handout. And answers can be concise, so you can, if you use more than 4 pages of your large book, then you're either writing very big or you're doing a lot of rough work on it. Yeah. Do I expect it to take the full 80 minutes? Yeah, I do. My exams are not short, but there have been students in the past who finished them in good time, but very few. So you can finish it very rapidly if you really know your work very well. Uh-huh.
But so the stability is the same for continuous and discrete, just the derivative.
No, it's not the same. It's the same in that you look at the derivative of the function, but the conditions on the derivative.
So what is the difference between the two? I thought they were both like you just solve the derivative and then you plug that, or you solve the equilibrium and plug it back.
Have you been looking at the notes?
Yeah.
Have you?
Yeah.
Okay. Have you been coming to class all the time?
Yeah, and outside.
Okay.
I guess I'm confused by that because it does this form, but I didn't see this form.
You haven't seen this form?
No, I've seen
Oh,
this form.
yeah.
And I'm trying to find this form, and I don't see it anymore. I see this one all the time. I know how to do both.
Yeah, no, I mean, in the beginning in the first months, we put this a lot when we went over the logistic harvesting, logistic equations, and all that. I mean, it's all there.
Yesterday in section, Paul and gave us a good list of things
Yeah.
we know, and they put up a section about yield curves, knife edge selection, sole ownership, and open source.
Yeah.
Is that in the lecture slides? Because I was unable to find it. I googled it and I went to your textbook, and I couldn't find it anywhere.
It's in the harvesting notes.
In the third lecture? I think the third lecture of harvesting. I couldn't find it anywhere.
In the harvesting notes?
Yeah.
Okay.
There's a lot of terminology that when I Googled it, like nothing
Yeah.
came out.
Oh, like which one? Yield effort curves.
Well, I looked for the yield effort curves for a while, and then I tried googling knife edge selections. That was one of the things I know pretty well. I couldn't find it anywhere in the textbooks and notes or the internet.
Knife edge selections in the harvesting notes.
It's like common pools, so source ownership and next size. I bet
Yeah, knife edge selections in the harvesting notes.
What about common pools?
Common pool.
Common.
It's common.
Oh, they put it on the board in the comma.
No, common. Okay, no, that's right. Yeah, you're not going to find common pool, right.
And that's in the third lecture? Because that's the third lecture of harvesting, I think. I looked at the third lecture. I couldn't find it, but like, I don't know, looking at it.
The yield effort curves.
Yeah.
Yeah, I guess,
Or was that later on? Is that like after?
no, I mean, there's some stuff that's just in the notes that I gave on the board. I mean, Colin Clark's book on mathematical bioeconomics is really the best place to find some of this stuff. Let me just...
Is that more or less the was kind of straightforward and findable?
Hastings theory. So, I mean, these curves are available to you. So what is it about yield effort curves?
Is this online?
This is in the harvest. This is in the notes. Well, firstly, it's in some of the lecture notes. Let's see. I'll tell you which lecture note it is.
Oh, it's in the ninth lecture. Maybe that's why I was missing it. I
Um,
think I was looking in the wrong place.
what do you mean lecture 9? You haven't got lecture 9?
To be honest, I thought it was only the first 8 lectures. So that's all I was
No, but I said 11.
Yeah, I know. Today you said 11. I didn't realize that.
No, I said it in the notes that I sent out about the exam. Yeah.
Okay. Well, anyway,
Yeah, no, I said, online, yeah. I don't know where you got 8.
misread it.
Yeah, but let's see.
I mean, if it's in the lecture notes and I was just looking in the wrong place, then I can find it.
Yeah, info on the midterm. Just want to check. Yeah, first 11 lectures.
That's weird. I read that very wrong. All right, thank you.
Okay,
All right.
okay.
I have a question on so in lecture 7, when you're doing the when
Yeah.
you're driving the formula and you do the optimal rotation period.
Yes.
This part right here is the derivative of VFT, right? From the VFT they give us here.
Yeah, which is S of t in the exam question.
I highly got this derivative because no matter how many times I went through the calculations and like, I plugged it in online, it just never gave me this.
On part A, let's see. Yeah, you got to differentiate
Yeah, so I
that.
mean, so we differentiate here, right? And so like you differentiate this to get this portion of the
Yeah,
equation, right?
yeah.
So I tried that like 100 times and like I plugged into like Wolfram alpha, but this equation never came out. It was like always something.
Yeah, so in Wolfram alpha, it may be the same equation, but it may be they may have multiplied some factors in and reorganized material.
I was getting like I did by hand too.
Yeah.
I was getting like t to like the 7 halves. It was like it wasn't 2 terms multiplied together. There was a minus sign between 2 terms because there's like a quotient rule. So I was just like I tried to get into this form, but I couldn't do it. I just couldn't figure out the math to get into that form no matter what I did.
Where does this come from? This is in the textbook.
Yes, I think so. It's you scroll up. That's
Yeah.
example 6.
If it's in the textbook, it's been checked by at least 5 different people.
No, I mean I'm sure this is
Yeah,
right.
no. I mean, sometimes there's a mistake. It could be, and there could be a mistake. All I'm saying is that the stuff in the textbook, there are mistakes, but every formula has been checked by 5 different people.
Yeah, no, so I'm sure it's right. I was just curious.
No, don't be sure it's right. You're 99% sure it's right.
I was
But
asking, like,
out of every 100 formula that you see, one could be wrong.
I was wondering, like, how exactly would I? Because, like, I just want to know, like, how would you get to that answer from this? Like, I do the derivation using the quotient rule, and like, I can just no matter what I do, because I know, like, for this problem, when I go through the steps that you gave us
Yeah.
in the beginning very portion,
Yeah.
it spits out something that you need to reorder into this, and
Yeah.
I figure out how to reorder it again.
Right, right.
So, like, I was just curious, like, 'cause I mean, I don't know, like, how to reorder it into this.
From part A, the specific form for VFT, the optimal rotation. So, yeah, that's VFT. Where's the formula that you get, that you've got to substitute it in?
This one right here.
Right, but where's the, using his formula, okay, using this technology, find the optimal and the discount rate is 0.1.
So, I mean, like, this is part A, so this is the formula that you just need to plug VFT into.
Yeah.
And so this is the derivative of VFT, so that's like
Okay,
the left
yeah.
side of the equation. So I just didn't
So-
have to calculate that derivative.
Is this the exact right-hand side without having done anything?
Correct, yes. So the right-hand side is just
Yeah.
VFT multiplied by this with substituting in gamma 0.1.
Gee, I mean, offhand, all I could do is work through it again myself and see, but I guess it's a harder example. I don't know what to say at this point.
So, like, on the test, like, if, like, 'cause I know, like...
You're not going to get anything that's complicated on the test.
Yeah, 'cause I know, like, your question
Yeah.
part 3 was, like, literally the exact same thing as part C here.
Yeah.
I was wondering, like,
Yeah.
like, how
Yeah, no, it'll be much easier.
Okay.
It's not going to, this is, let's see what, yeah, this function is much more complicated than the one you'll get. What did we choose it equal to here?
0.
Yeah, that's,
Yeah, and I mean, yours, it was, like, gamma equal to 0 or something like that. So.
yeah, it's going to be just a simple square root.
Okay, awesome.
It's going to be, yeah. So, yeah, anything that I do in the exam, you don't really need Mathematica to,
Okay.
yeah.
I was...
Yeah, sorry, I'm sorry you can't work that out, but,
I just want to know, like, my own...
yeah, no, it should work out, and you got, yeah, as I said, these formulas have been checked by several people, but there could be a mistake.
Yeah.
And I could take a look at that again.
Oh, actually, sorry, can I ask you one
Yeah,
more?
sure.
So this is actually in your portion of the notes.
Yeah.
So I know Colin stuff had, like, put out the notation with, like, the notation.
Yeah.
But my question was more in... So you have this whole notational thing where
Yeah.
T is element of 0, and then you move from P of n t plus t to this. You condense it down to just P of n capital T. Where does the little t go?
This is just saying that it's periodic, but we're only interested in it when t is equal to at the periodic points.
Oh, okay. So then what you...
We're only interested in it we're only interested if you go up here. We're only interested in it at these discrete points. So we're only looking at that, putting at these points.
Right.
And so it's the same at each one of those points.
Okay.
Yeah, yeah.